Your computer runs on two states, 0 and 1. You've heard that 1,000 times. But here's what nobody tells you, it almost ran on 3. And the machine that proved 3 could work? It wasn't built in Silicon Valley. It was built in Soviet Moscow, and it beat its binary rivals at their own game. This is the story of ternary computing, the road not taken. It's a forgotten chapter of hardware history, and once you understand it, you'll never look at binary the same way again. So let's start with the obvious question. Why 2? Why did every computer on your desk, in your pocket, and in the cloud settle on just 0 and 1? The standard answer is reliability. A transistor is basically a switch. It's either on or it's off. High voltage or low voltage. Two clean, distinct states that are easy to tell apart, even when the signal is noisy and messy. But that answer hides something. 2 isn't actually the most efficient base for representing numbers. Not even close. Here's the math that breaks people's brains. If you want to store numbers efficiently, the theoretically optimal base isn't 2. It's the mathematical constant e, roughly 2.718. You can't build hardware around an irrational number. So you round. And the nearest whole number to 2.7? It's 3. Not 2. 3. In other words, by pure information theory, a 3-state system packs more meaning into fewer digits than binary does. Ternary is mathematically more elegant. So why didn't it win? To answer that, we go to Moscow State University in 1958. A young engineer named Nikolai Brusentsov is about to build something the West will spend decades pretending didn't happen. Brusentsov and his team built a computer called Setun, named after a river near the university. And Setun didn't use bits. It used trits, ternary digits, each holding one of 3 values. But here's the genius part. Setun didn't use 0, 1, and 2. It used -1, 0, and +1. This is called balanced ternary, and it's quietly beautiful. Why is balanced ternary so clever? Because negative numbers come for free. In binary, you need special tricks like 2's complement to handle negatives. In balanced ternary, a negative number is just the same number with its signs flipped. No special case needed. Rounding also becomes trivial. To round any number, you simply chop off the last trit. The system rounds correctly by design. Engineers who worked with it described the arithmetic as almost suspiciously simple. And Setun worked. It really worked. It was reliable, it used surprisingly few components, and it was cheap to build. Around 50 of them were manufactured and shipped across the Soviet Union and beyond. Universities used it. Engineering labs used it. It taught a generation of Soviet students how to compute. By the standards of its era, Setun was a quiet, genuine success. So now we have a real paradox. A more efficient number system. A working machine. Proven reliability. Lower cost. Why on earth did binary crush it? The first reason is brutally physical. Building a stable third state is hard. A transistor naturally wants to be fully on or fully off. Forcing it to sit reliably in a middle state means tighter tolerances and more complex circuitry. With 2 states, you get enormous noise margins. Voltage drifts a little? Doesn't matter, it's still clearly on or clearly off. Add a third state in the middle, and suddenly your safety buffer shrinks. Noise that binary shrugs off can corrupt a trit. So the theoretical efficiency of ternary got eaten alive by the practical messiness of electronics. On paper, 3 wins. In silicon, 2 is just easier to keep correct. But the deeper reason isn't physics at all. It's economics and momentum. And this is where the real lesson lives. While Setun was running in Moscow, the West was pouring billions into binary. Bell Labs, IBM, Fairchild, and the entire emerging chip industry standardized on 2 states. Every tool, every fabrication process, every textbook assumed binary. Once an industry commits to a standard, that standard compounds. Better binary chips made better binary software, which justified more binary chips. Ternary never got that flywheel. It was a better idea with no ecosystem behind it. This is what economists call path dependence. The winning technology often isn't the best one. It's the one that got enough momentum early enough that switching became unthinkable. You see this pattern everywhere in tech. The QWERTY keyboard wasn't designed for speed. JavaScript wasn't designed to run the world. They won because they arrived, got adopted, and then the cost of replacing them grew faster than anyone's appetite to try. Setun was caught on the wrong side of that curve. Soviet planners eventually wanted to standardize on binary machines to match the global ecosystem. Funding dried up. Production stopped. The ternary computer was quietly retired. And here's the twist that makes this more than a history lesson. Ternary keeps coming back. Researchers exploring new kinds of memory and chip design occasionally revisit multi-state logic, because as transistors hit physical limits, packing more values per element starts to look attractive again. Some experimental flash storage already stores multiple voltage levels per cell, which is multi-state thinking sneaking in through the back door. The idea Brusentsov championed was never wrong. It was just early, and unlucky. So the next time someone tells you computers use binary because it's simply the best way, you'll know the fuller truth. Binary won because it was good enough, easy to build, and first to scale. Not because 3 was impossible. The thing developers treat as a law of nature, 0 and 1, is really a frozen accident of history. A choice that hardened into bedrock. And somewhere in an alternate timeline, programmers are debugging trits and wondering why anyone would settle for just 2.